This video is brought to you by mywayteaching.com.
So, in this particular part, let us study gravitational potential energy. So, we have already discussed earlier the motion of potential energy as being the energy stored in the body at its given position. So, potential energy is by virtue of its position. If the position of the particle changes on account of forces acting on it, then the change in its potential energy is just the amount of work done on the body by the force. Okay, whenever a position changes, the change in potential energy takes place, isn't it? So, that change in its potential energy is just the amount of work done. So, it is amount of work done on the body by the force. Okay, forces for which the work done is independent of the path, they are called as conservative forces. Okay, forces for which the work done is independent of the path, then they are called as conservative forces. The force of gravity is a conservative force. Okay, because we can, it is independent of the path, and we can calculate the potential energy of a body arising out of this force, that is called as gravitational potential energy. So first of all, the force of gravity, this is a conservative force, and we can calculate the potential energy arising from this, that is called as gravitational potential energy. Consider the points which are close to the surface of the earth at distances from the surface much smaller than the radius of the earth. So, if this is the surface of earth, then you just consider the points which are very close to the surface of the earth. This distance, the distance between this point and the surface of the earth must be much smaller than the radius of the earth. Okay. And in such cases, the force of gravity is practically a constant and it is equal to mg. If that points are very close to the surface of the earth, then in that case the force of gravity will be constant and whose value is equal to mg. Directed towards the center of the earth. If we consider a point at a height h1 from the surface of the earth and another point vertically above it at a height h2 from the surface, the work done in lifting the particle of mass m from first to the second position is w12. So again, if we consider two points above the surface of the earth, one is somewhere here and one more is at a, okay, somewhere here. So one is at a height h1 and the other one is at a height h2. Then the work done in lifting the particle of mass m from first to the second, that is given by w12, and that is equal to force into displacement. So that force is mg and the displacement is h2 minus h1. Okay. If we associate a potential energy W of h at a point at a height h above the surface of the earth, so at that time we get the potential energy that is equal to mgh, because the point is at a height h above the surface of the earth, plus W naught. So where W naught is a constant. So it is very much clear that the W12 is equal to W of H2 minus W of H1. So the work done in moving the particle is just the difference of potential energy between its final and initial positions. Okay. So in this particular equation, W not cancels out. If in this particular equation that I just considered, this W not cancels out. Setting H is equal to 0, we get W. If you set H is equal to 0, then we get the value which is equal to W naught. H is equal to 0 means the point is on the surface of the earth, thus W naught is the potential energy on the surface of the earth. If we consider the points at arbitrary distance from the surface of the earth, then the result just derived is not valid. Since the assumption that the gravitational force mg is a constant is no longer valid, that is constant only near the surface of the earth. However, from our discussion, we know that a point outside the earth, the force of gravitation on a particle directed towards the center of the earth is given by F is equal to G m e m by r square. So where me is mass of the earth. Okay, and m is mass of the particle. And r is the distance from the center of the earth. If we calculate the work done in lifting a particle from r is equal to r1 to r is equal to r2, where this r2 is greater than r1 along a vertical path, then we can write W12 is equal to minus G m e m 1 by r2 minus 1 by r1. So the potential energy at a distance r, we can write it as minus G m e m by r plus W1, which is valid for r which is greater than capital R. So once again we can write W12 is equal to W of R2 minus W of R1. Setting R is equal to infinity, in the previous equation we get W r is equal to infinity, if you set, then we get W is equal to W1. So this W1 is the potential energy at infinity. Okay. One should note that only the difference of potential energy between 2 points has a definite meaning. So we can set W1 equal to 0, so that potential energy at a point is just the amount of work done in displacing the particle from infinity to that point. So we have calculated the potential energy at a point of a particle due to gravitational forces on it, due to the earth, and it's proportional to mass of the particle, isn't it? So the gravitational potential due to the gravitational force of the earth is defined as, okay, the gravitational potential due to the gravitational force of the earth is defined as potential energy of the particle of a per, okay, of unit mass at that point. From the potential, okay, from the potential energy associated with two particles of mass m1 and m2 which are separated by a distance r, in that case that is given by minus g m1 m2 by r. So if we choose v is equal to 0, then r tends to infinity. An isolated system of particles will have the total potential energy that equals the sum of energies for all the possible pairs of its constituent particles. Okay. Now let us solve a very simple problem. Find the potential energy of a system of four particles which is placed at the vertices of a square of side L. So obtain the potential at the center of the square. You just consider this square for the reference. Consider the four masses, each of mass m, at the vertices of a square, and the length is given by L, isn't it? We have four mass pairs at distance L, and two, we have this two which are represented with the diagonal pairs. They are at a distance square root of 2 into L. So we know the equation W of R is equal to minus, here it is 4 gm square by L minus 2 gm square by square root of 2 into L. If you take minus 2 gm square by L common, then the value we get is minus 5.41 gm square by L. So the gravitational potential at the center of the square, where R is equal to root 2 L by 2, that is given by minus 4 root 2 g m by L. Okay, this is the gravitational potential at the center of the square. The gravitational at that point, the value of R is taken as root 2 L by 2.